thank you for being here. I'm part of the Visualization Interactive HPC team at JSC and permanent staff there. And so we are trying to make things possible while playing with the toys, which are the big systems. And so visualization, or I would say interactive in-situ analysis. So if visualization or analysis, don't want to make that big of a difference there, but is a topic. It's a big topic, thinking about the amount of data we have to move and work with. So that's what we are thinking of, and of course, in the whole context of the new system. So sure, we are hoping that with the new system, there can be much more, from a scientific point of view, much more, getting much more insight from the data. And in the background, one has to kind of test and come up with solutions which provide that. And we are in close cooperation with, of course, a lot of users on the system. And here I'm happy that we have setups and use cases from them. And what I'm also talk about is data set from Russia there. So you already know quite a bit about the data, and I will more talk about the workflow around that. And we are in close cooperation with Argonne here when it comes to developing these workflows, especially when it comes to NekRS, developing these workflows. And I'm quite happy that these cooperations started actually last year in a way that we really meet and discuss and develop solutions for future big systems. And yeah, so when one talks about in situ visualization, in situ analysis, one always says the same, comes up with the same motivation, and people are kind of hearing this motivation now since 20 years. Yeah, there will be so much data, you will never be able to put it in storage. And actually, it's true, but I'm a little bit worried if someone kind of gets afraid when they hear, oh yeah, we need to jump on in situ analysis, in situ visualization soon, if this kind of motivation has been there for these many years. And with every new system, of course, the challenge gets bigger and bigger. We know that the CPU and I/O gap is increasing, but we even though I would like to point to a few numbers from the new system, and Benedict already showed these sketch here, these image here, and I highlight a few things which might be reasons to get a bit worried at least. Thinking about the bandwidth between the GPU and memory on the GPU with 4,000 gigabyte per second, there's really a lot of data we can move there. Of course, there are kind of bottlenecks at some other places of the whole infrastructure, but we really have the chance to get a lot out of the data as long as we try not to move it too much. Yeah, so bottom line, how in situ visualization, in situ analysis is something to think about. And looking at the past, it was always kind of more of a hassle to get it up and running. And there have been multiple solutions over the years. I actually jumped in with Visit. So somewhere there, 2011, Visit LibSim. And at the same time, ParaView Catalyst also started with their quite prominent solution with which I would call Catalyst 1. And yeah, it was already fun at that time, actually doing it already with quite big data sets. But it was kind of apart from the normal a road or workflow which one goes through when analyzing data. It was always some kind of extra stuff. For Catalyst 1 and also for LibSim, one needed to add quite some extra code in the simulation, and therefore it was the coupling between the visualization and the simulation was always an issue there. We see that we went on with Sensei here, as there was a big drawback that with the first two, Catalyst 1, LibSim, one was kind of fixed to the ParaView or visit, and Sensei was allowing or is allowing to choose whatever endpoint one wants to use. And yeah, so we will talk a bit about the advantages when it comes to your setups like Ascent and also Catalyst 2. And one important software package for in-situ or in-transit setups here is Adios. That's at least what we are working to do, the communication between the simulation nodes and the visualization nodes when it comes to in-situ, in-transit visualization. So having a look at Sensei, that's what we worked on last year actually. It gives the big, or it came with the big advantage that one had the ability to implement these coupling structure once in the simulation code, and then can provide the data to multiple endpoints here from Catalyst, Visit, also through Adios or Python, YT, and so on. So that was or is still a big advantage, and after compile time, at runtime, you can select which endpoint you want to choose. Developed here at Lawrence Berkeley National Lab, open source, and yeah, you might have heard about it. These advantages come with one kind of I would say the drawback here is that we are still stuck also with the same as with ParaView Catalyst 1 and also with Visit LibSim, that we have to reorder our data structure in memory, or at least most of the time, and here to a VTK data structure. But if you once have done that, then you are quite flexible. And if you check here how the Sensei analysis adapter look like, kind of actually easy to implement, but of course you have to be close to the simulation developers, and then can add these adapters, and at runtime you can switch between the endpoints. This Sensei setup we tested with NekRS, and as I said, advantage is write once, run anywhere. For and here in this setup, we have shown that at the supercomputing last year at an in-situ workshop. This setup ran on Polaris at Argonne, showing actually what one is hoping to see, especially when one looks here at the memory footprint for using Catalyst or for checkpointing. One compares that for different kind of setups, 70 nodes, 140, 280 nodes, that one kind of sees that the memory footprint between Catalyst and checkpointing is say predictable, and more important when it comes to time to solution, that for checkpoint one kind of has almost, or it's kind of similar time to do a checkpoint than to use Catalyst to write down one image on disk. We at the JSC, we looked in the in-transit setup, and thinking about in transit setup, the advantage here is sure you're fighting for the same resources if you do visualization on the compute node and simulation on the compute node, and therefore if one kind of separates that to special visualization nodes, these kind of resources are then dedicated to simulation visualization, and a few things are getting more easy to do, especially in production setups. And therefore, Sensei also comes here, as I already said, with an ADIOS interface, and so one can couple kind of two layers and go from the simulation to ADIOS, send it to some other node, and then into whatever visualization tool one wants to use. And also that kind of is what one expects. Memory footprint is the same for all configuration, thinking of weak scaling, and time per time step also is the same for checkpointing and Catalyst. But actually, the big drawback which comes with Sensei is that you're still stuck to VTK data structures, and therefore have to convert your data structure in memory to VTK. And probably one also thing which is a drawback is there's further funding situation is unclear for Sensei. So it's also from that point of view a good idea to check what are the alternatives, and to think of the first kind of challenge: how can we avoid that we have to rewrite our data in memory? Conduit is the solution for Ascent and also for ParaView Catalyst 2. It's kind of a description language for your data in memory, and at least I can still remember XDMF, which was doing kind of the same for data sets which were written in HDF5. So one could dump the data and afterwards describe it in some kind of XML language. And here Conduit is doing kind of the same for running simulation, and therefore one do not have to kind of convert the data, and also there's no need to have extra the VTK linked to your simulation. And the separation of simulation code developers and visualization code developers is more strict. And yeah, with Ascent, this works quite nicely directly from the terminal. There's no graphical user interface, but if one is kind of used to writing pipelines as some JSON file or YAML file, then that works out and was doing a good job for us here. So we have run that setup, and Roshan already showed a few things from that. Of course, we want to go for the bigger the better, and seeing what are the challenges there, not just the challenges setting it up once, but also the challenges if you're really doing production runs on that. And with these combination, Ascent and NekRS here in-situ, so you're running on the same node, Ascent and NekRS, it was working surprisingly well, to say. There was not that much of kind of tweaking needed. Of course, we had to ensure we are, as I said, when one competes in compute resources, especially in memory, main memory, have to have an eye on that. And so we could run it on the whole Joules booster here. And as you can see here from the job report, that we're using here, what is it, 83% average GPU usage. So the whole setup was running on the GPU. Ascent is made for that and was doing just a great job here. We all have already seen this visualization, and the nice thing on Ascent is that while your simulation is running for quite a long time, you can tweak with the YAML file and get updates of your setup in a way which is kind of, I would say, HPC user friendly. There's no GPU, no graphical user interface, but from the point of an HPC user, that's kind of an easy setup. And yeah, the implementation looks, when it comes to Conduit, looks a bit like this, describing the memory and then passing it to Ascent. And so passing only a device pointer to Ascent, there's no copying of the memory needed. And in our setup, we just create an image every 100 time steps. And to describe then the pipeline with these YAML files was also something to easily pass along, also when it comes to multiple people who are working on the setup. But of course, there is always overhead. You don't get it for free. And looking at the overhead, we had here where we were dumping every 100 time step an overhead of 16% on our system. And one can also compare the setup without Ascent and with Ascent. Perhaps you can see it a bit that if you are running your code here, the time goes from left to right, and on here you see the different nodes, and the memory usage is colored in this image, so you can see the memory usage used on the GPUs, and you can see that when you don't run any visualization, it's quite a straight line. As soon as you run any kind of Ascent on top of that, you can see that these light blue, the memory consumption sometimes peaks up, and of course you should not hit the top roof or your code will crash, and so they're kind of disturbance at not only memory but also at the compute time, and so that's the drawback of In-situ here, which one can cope with if one is not kind of playing too much with the pipeline while the code is running. So we're pushing that forward, thinking of the big simulation especially. So if you are interested in going for really large scale and want to do in-situ analysis in transit analysis, we are highly interested if you are sure, if you are kind of have access to our systems to push that further. Next step is currently to combine in-situ and in-transit, thinking of data compression on the compute node and then the visualization actually on other nodes. And we need to kind of get this into production away from more the exotic cases. And therefore, yeah, we are hoping that this can become a standard workflow, at least an easy workflow on Jupyter. Thanks. That's it.